So at the end of the previous video, we introduced the mean value theorem a little bit hurriedly, but it's a really important result, so I want to recap it quickly in the beginning of this video. It says that for a function f that's continuous on a closed interval ab and differentiable on that open interval, then there's a c within this interval that's open such that the slope of the tangent line at that point c is parallel to the secant line connecting those two endpoints. And that's written out in mathematical language as f prime of c is equal to f of b minus f of a over b minus a. Again, this is that delta y over delta x slope of the secant right here, and f prime of c is going to be the slope of the tangent line. And so you can see that no matter how many or how close you zoom in to any given interval, you'll always find such a situation. So as you can see on this graph here, the endpoints are here a and b, and we've seen that if we connect the secant, we found 2 points here that have tangent lines that are parallel. But what if I zoom in even closer? What if I take these two C points and I make a tangent or secant between those two? Well, take a look. It looks like there's a line somewhere right here that's parallel to those. Okay? And so that's how this statement is true, the mean value theorem. No matter how close you zoom in, you can take these two intervals, connect them as secant, and there's still going to be a line that's parallel that's also tangent. So that's a really profound result in calculus. And that's just something I wanted to kind of elaborate on a bit more. But the goal of today's video in real terms is to get an idea of what a function could look like on a graph without actually knowing what that graph looks like, and rather just its equation. And we're going to start that by figuring this out by using and taking a visual exercise. We're going to think about a function that's increasing and or decreasing. So let me bring back my friend sine of x, okay? F of x is equal to sine of x. We know what that graph looks like. And if you didn't, then the things we use in today's video will help you know what the graph looks like. So here you go. Now, when is a function increasing and when is it decreasing? Well, we know that a function is increasing by definition if consecutive values are greater, okay? Which means that f of x2 is greater than f of x1 when x2 is greater than x1. That just means consecutive values of the function are greater. As you can see on the interval from 0 to pi over 2, this function is increasing because it only gets greater. All right, and the analogy here is similar to if you've heard of the idea for continuity, where if you can draw a function's graph without picking your pen off the paper, it's continuous. In a similar way, a function is continuous on a certain interval if when you're drawing that function on the interval, your hand never goes below a previous point that your hand has reached when drawing it with the pen. All right, and likewise here, sine of x is decreasing on this interval from pi to 3 pi over, or from pi over 2 to 3 pi over 2. Because when we draw it with our pen, we never go above any previous points we've covered with our hand and the pen. And that's written out in math terms as f of x2 as a consecutive term is less than f of x1 when x2 is still greater than x1. So watch out for that. x2 is greater than x1 because we're just moving along the x-axis, but consecutive values are now lower, thinking about it like a strictly decreasing or increasing sequence. But in total, there's areas where sine of x is increasing, like over here, decreasing here, and increasing again. So that's the idea there. Now, if you take a look and try and connect this to derivatives, which is, again, the whole point of the first application of derivatives with maxes and mins, we can see that the tangent lines on a function that's increasing on the interval always are positive. And if that's a conjecture for what's true, then you're right. It is true that a function increasing on a certain interval will always have a positive derivative on those intervals. So let me write that out. And I give you some examples here. So we have an example of arctan of x, the inverse tangent, okay? This function is strictly increasing on its domain, all right, which is negative infinity to infinity. And we know we've got the asymptotes at pi over 2 and negative pi over 2 like this, all right? And drawing it out, we get this. Again, our pen is never going back down. And so that's our function arctan. And if you take the derivative of arctan, so d dx of arctan of x, and I encourage you to look at the previous video that we've made on Josh Academy explaining how to take the derivatives of inverse trig functions, we get 1 over 1 plus x squared, and this is actually never negative, which explains why this function is increasing everywhere. All right, another example we have is e to the negative x. All right, this function is always decreasing because e to the x itself is positive. E to the negative x just looks like this. As you can see, the tangents are always negative sloped. And when you take the derivative, you get d dx of e to the negative x, all right, is equal to, by the chain rule, we have the negative 1 hops down, we have negative e to the negative x, all right? And that's going to be basically a reflection of this across the y-axis. It's going to look like this, all right? And that's always negative, and that's why this function is always decreasing. So that's some good explanations there as to why that's true. Okay, now let's actually formalize that, okay? We know that whenever the function is increasing, the tangent slope is positive, and so f prime of x within that interval, I'm going to write here, within that interval, a function's increasing, so here's our interval, and a function's increasing on the interval, a to b, all right, if f prime of x is greater than 0 for all, this upside down a is for all x within a and b, like this. And if it's decreasing, then of course f prime of x has to be less than 0 for all x within that interval a, b. So I hope that that gives you a good idea of what it means to be increasing or decreasing. As you can see, we've done that with the e to the negative x, where the value of the derivative is always negative, and the value of the derivative of arctan is always positive, which gives us a sign of what they're doing with their increasing and decreasing. Another example in statistics, you see the bell curve, okay, which is given by the graph of, or in the function e to the negative x squared, all right, and that's going to be itself always positive, but as you can see, it's increasing visually over here on the from negative infinity to 0, like this, and then it's always decreasing for the rest of that journey from 0 to infinity. And indeed, when you take the derivative of that function, so you get, let's see, you get negative 2x e to the negative x squared by using the chain rule, then whenever x is negative, these two negatives cancel out and it becomes positive, which means it's increasing, and we can see that here. And whenever x itself is a positive value, nothing cancels out that negative sign, which means it's going to be negative, and so the slopes are always negative. So there's a good idea of those derivatives in action. All right. You can also prove this idea using the mean value theorem, which is sort of why we went over again in the beginning of the video. All right. Let's take a look at another important piece of information with functions, that being concavity. Now, in your Algebra 2 class, you may have heard up like a cup, down like a frown. All right? It's concave up when it's up like a cup, and a smiley face, or down like a frown, and it's a sad face. And this is more accurate if you say up when second derivative is greater than 0, and down when second derivative is less than 0. Which is right. If a function f is twice differentiable, all right, which means that you can take the derivative twice, on a certain interval ab, okay, then the second derivative gives us information about the concavity. So we say that a function is concave up, so f is concave up on ab if, all right, f double prime, the second derivative of x, is going to be greater than 0 for all x within that interval ab. And then f is concave down, all right, concave down on that interval ab if f double prime of x is less than 0 for all x within ab. And you could also prove this, but it's also a really nice visual argument. And that's what I'm going to give you right here. Let's write visual argument. This is a really important visual argument, and I want you to do your best to try and understand this. But we're going to reverse engineer it, okay? Let's see if f double prime is greater than 0 on a certain interval, then on the line here on the x-axis, it's going to look like it's going to be somewhere positive like this on an interval ab. So here's one of our endpoints, a, then b. So as you can see, it's always positive. Now, using what we've learned about increasing and decreasing functions, we know that if we draw the graph of f prime in this area of ab, all right, in this interval, then because f double prime is always positive on that interval from a to b, then f is increasing on a to b. So it maybe looks like something like this, all right? The tangent is always going to be positive, and that's why the area right here of f double prime is going to be positive. An area not as in the area under a curve or anything. I'm just talking about this domain, this interval. All right, and now we can also reverse engineer this back to the original function f. Now if f in that area here, in this little domain, I should stop calling it area, but the little interval, we can see here that f prime is negative in some areas and it's positive in other parts of the interval, which means that the actual nature of whether f is increasing or decreasing changes. So here, from this point up here to a, the function is negative, which means f is decreasing from that little point, which means it's going to be something like this. Let's see, a goes like this maybe. And then from here to b, this derivative is positive, which means it's increasing. And lo and behold, you see that over here, we have that up like a cup. So f is concave up when the double prime is greater than 0. So that's the important visual argument. Now, if we do f double prime is less than 0, what do we get? Well, if we graph that on that kind of interval a to b, then if it's less than 0, then we see something sort of like this. And when we reverse engineer that to f prime, we can see that since it's always negative, then f prime is always decreasing, okay? Which means we can draw some decreasing function or some decreasing behavior like this, all right? Or better, something like this, all right? It's always decreasing. Now, that means that there's parts that are positive and parts that are negative. But in this case, it's kind of the flip side of what happens with the previous case when f double prime was positive. Here, if we draw the actual function f on that interval a to b, then there's some parts, again, of f prime that are positive, which means the function's increasing on those points. So we have a function, maybe it looks like this on that point, up until this point here, when it's a maximum, if you will. And then we see that the f prime is negative for the rest of that journey from that little center point to b, which means that the function f is decreasing there. As you can see, we can have the down like a frown. We see that concave down. And there's your visual proof or visual argument for why the second derivative gives us this information. So that's a really, really nice example and really nice visual argument. And we're going to go into this a little bit later in the next video. What happens, however, if f double prime is equal to 0? Well, our test fails. The concavity test will fail, and we can't really say anything about the concavity of the function. Now, another way you can find out if a function is concave up or down using visual arguments is take this function, for example, like this. A function is concave up on a certain interval if the tangent line is always below the graph. As you can see here, it's concave up like a cup, and the tangents here are always below the graph. And it's concave down like a frown here when all those tangents are above the graph. So that's another nice visual interpretation if you need one. All right, now we're going to use what we've learned about concavity and increasing and decreasing functions to sketch the graph of a function that we don't really know what it looks like. If we have f of x is equal to the natural log of 1 plus x squared, I bet you can't just tell me right away what that looks like in the next 5 seconds. Instead, we're going to have to learn something else about its behavior. So first of all, we want to look for some interesting points. So obviously at x equals 0, we have the log of 1, which means we have 0. So that's some important information. But let's see if this function is increasing or decreasing anywhere. We know that the function is increasing when the derivative is greater than 0, and it's decreasing when the derivative is less than 0. So let's take the derivative. F prime of x is going to be equal to, well, the derivative of the log of 1 plus x squared is going to be 1 over 1 plus x squared multiplied by the derivative of the inner function, which is going to be 2x. So we get 2x over 1 plus x squared. Now remember, 1 plus x squared is always a positive part, but x here can be negative or positive. So we can see that f is increasing, all right, when it's going to be a positive derivative. So it's increasing on the idea on the graph of 0 to positive infinity, all right, and it's decreasing on negative infinity to 0. All right, and I encourage you to kind of finish the rest of this idea and finding the increasing and decreasing in concavity. Now, where are their critical points? Where are their criticals? Well, when this is equal to 0, there's only one answer, at x, when it's equal to 0. So we know that x equals 0 is a critical point. It's a critical. So that's going to be important for us in our analysis of this function. Now, how about the second derivative to determine concavity? F double prime of x. Well, let's just use the quotient rule here. We get f prime g minus g prime f. So f prime is here is 2 times 1 plus x squared. So we have 2 plus 2x squared minus g prime f, which is going to be, well, here it's going to be 2x times, again, 2x. So it's minus 4x squared. And we take that divided by g squared, which is this entire expression here. 1 plus x squared squared. And we get, ultimately, we get 2 minus 2x squared over 1 plus x squared quantity squared. Now, of course, this remains a positive part, and so the only thing we have to worry about with positives and negatives is the upper part. When is that less than 0, and when is that greater than 0? So if we do 2 minus 2x squared is greater than 0, we get 2x squared is going to be less than 2, which means x squared is less than 1, which means the absolute value of x is less than 1. So we know that this function is going to be concave up whenever absolute value of x is less than 1. Well, what does that mean? Well, it's concave up on the bounds of negative 1 to 1. And you'll see why we include the negative 1 to 1 later when it says less than. All right? So it's negative 1 to 1. So let's see. Concave up. Conc up on that. And when is it concave down? Well, 2 minus 2x squared is going to be, let's see, less than 0. So that means 2x squared is greater than 2. Cross out those 2's. And we have x squared, or let's take the root of that already, and absolute value of x is greater than 1. So it's the rest of the domain that's not this. And so we see that f is going to be conc down, so concave down like this, on two intervals, okay, that are unions. We have negative infinity to negative 1, like this, union 1 to infinity. And so now we have a lot of good information as to how we're going to graph this function. So let's do that. Here's our graph. And we know that, first of all, plotting some important points like our critical point here, it's x equals 0. It's a critical. So we have 0, 0 as one of our criticals. Now, we can also see that the actual function itself, ln of 1 plus x squared, is going to be increasing on 0 to infinity, which means we're going to have some sort of behavior where it's going to be getting bigger and bigger. But it's also increasing, or it's actually decreasing on negative infinity to 0, which means we're going to have negative tangents, of course. So we have this sort of behavior first. Now, why am I not filling this center part? Because this is where the concavity happens. We have concave down on negative 1 and 1, which means that, or sorry, I should say, concave down on negative infinity, negative 1, union 1 infinity. But we have concave up on negative 1 to 1. So we have some sort of up like a cup behavior over here. And then it changes concavity on the other endpoints like this. So here's a good estimate. And here's a good estimate of what the natural log of 1 plus x squared looks like. We filled out the points. And you can see here that the point x equals 0, and so it's 0, 0, is an absolute minimum. And now, if we look at the points 1 and negative 1, the points where they change concavity, those might be interesting points too. And in fact, when you plug them into the second derivative, 1 and negative 1, you'll get 0. So technically, our second derivative test fails there. But that also means that this gives us some information on the function changing concavity. The points where a function changes concavity are defined to be called inflection points. All right, inflection points. And we've seen inflection points before. You may have heard of them in your Algebra 2 classes, but inflection points are essentially points where the function changes concavity. So let me give you the most famous example here, our good friend x cubic, all right? So here, the tangents are always above the graph and then they go below the graph. So the point 0, 0 is an inflection point. Or sine of x, it has infinitely many inflection points, all right? So let me give you some examples like here. So here, the tangents are below and then they go above at 0. So 0, 0 is also an inflection point. Here they're above and then they go below the tangents. And so what you get is that the x equals pi is also an inflection point. And so the inflection points of sine look like 0 plus pi k, where k is an integer. All right? So those are the inflection points, the x coordinates of the inflection points for sine. Okay, so I hope that this has given you a nice idea of how we use first and second derivatives to discover a lot of important information about functions. And next up, we're going to do even more second derivatives and beyond. See you then.